I'm Rayesh Uppal, founder of IDST. We bring you sharp insights and foresight on emerging tech, defense, and security. Let's
Imagine a
dive in.
computer so powerful that it could design new drugs in days instead of years, discover new materials at the atomic level, optimize entire supply chains instantly, and solve problems that today's supercomputers can't even touch. That's the promise of quantum computing. But here's the catch: it's one thing to dream about the potential, and quite another to measure how close we really are. That's where DARPA's quantum benchmarking program steps in, with the ambitious goal of creating real, practical metrics to track quantum progress, and to answer the ultimate question: when will quantum computers be ready to change the world? Quantum computers are fundamentally different from the machines we use today. Instead of bits that are either 0 or 1, quantum bits or qubits can exist in many states at once, thanks to the strange rules of quantum mechanics. This allows them to explore countless possibilities in parallel. Add in quantum entanglement, and you have systems capable of solving problems at a speed classical computers can't dream of. The implications are huge, from breakthroughs in artificial intelligence and big data, to quantum chemistry simulations that could transform medicine and clean energy, to solving complex optimization puzzles in logistics, finance, and even protein folding. But there's a big challenge. Nobody really knows how large, how powerful, or how reliable a quantum computer needs to be to achieve all this. DARPA's quantum benchmarking program is tackling that head-on. The idea is simple but profound: develop benchmarks rooted in real-world problems, not just abstract math, and estimate the actual resources, both quantum and classical, needed to solve them. This means setting practical milestones, instead of just waiting for some undefined quantum breakthrough moment. The program launched with a wide lens. In its first phase, teams gathered over 200 potential applications for quantum computing and narrowed them down into about 20 candidate benchmarks. These weren't just theoretical, they focused on chemistry, materials science, and complex equations that underpin some of the hardest problems in science and industry. Now in Phase 2, DARPA has selected a handful of these benchmarks for deep study. Teams are refining resource estimates, running scalable tests, and analyzing how quantum systems stack up against today's digital supercomputers. Some of the early findings are already fascinating. For example, quantum simulations could make chemical catalyst discovery far more efficient, saving industries huge amounts of time and cost. In fluid dynamics, which is notoriously expensive to simulate, quantum methods could one day reduce the need for trial and error testing in aerospace and naval design. Even in medicine, quantum models could improve nuclear magnetic resonance analysis, giving scientists clearer insight into molecular structures and accelerating drug development. Of course, challenges remain, like dealing with errors and ensuring fault tolerance. Programs like Riverland's work on the surface code are exploring exactly how much overhead is needed for error correction, and what that means for the real-world size of usable quantum computers. Other research is pushing into strongly correlated systems in physics and open quantum simulations of exotic materials. All of this helps us move from hype to hard numbers. How many qubits do we need? How accurate must they be? And what kinds of problems will they solve first? The quantum benchmarking program isn't just academic. It's about providing a roadmap, a way for policymakers, industry, and researchers to see where we are going and how fast we can realistically get there. Because in fields like healthcare, energy, and national security, knowing when quantum advantage will arrive is just as important as knowing what it can achieve. So while the world buzzes about quantum as the next big thing, DARPA is laying down the yardstick to measure progress. By defining clear benchmarks, resource requirements, and performance metrics, the program is shaping the future of quantum computing into something practical, not just theoretical. And if successful, it could mark a turning point when quantum computing moves from possibility to reality.